Hello and welcome to this Sustainable Manufacturing Laboratory. My name is Shahin Rahimifard. I'm a member of the staff in WolfsonSchool of Mechanical, Electrical, Manufacturing Engineering. Sustainability is now a subject that doesn't need introduction. In the last 5 or 6 years, we've seen a significant interest and focus on various activities to do with climate change and global warming, where the subject of sustainability now has become one of the core subjects within engineering education. To be fair, at Loughborough, we have been teaching about sustainability and impact of sustainability in engineering for the last 25 years. And our activities, both in research and in teaching, has obviously evolved over these 25 years to the extent that our Sustainable Manufacturing Laboratory now has been divided into 3 distinct hubs, where there is this, which follows the life cycle of a product. So we have a design hub, a manufacturing hub, and a recycling hub. Within our design hub, basically what we do is we investigate the redesign or the new design of a product to lower the impact of either an industrial product, like for example this engine management system for an electrical car, or a consumer product like this vacuum cleaner. So if it's a redesign of an industrial product, the function is typically start with manual disassembly of the product to identify the various components within them, look at the design, where the different materials been used, how difficult it is to get into it, what are the consumables, how would you repair it. And the focus of redesign is obviously to make the disassembly easier. By doing so, what you do is you make the repair of the product more feasible, more possible, i.e. extending the life of the product. And the other is at the end of the life, when you need to recycle the product, the idea of separating a material and then individually treating them gives you better quality of recycled material that you can use in other application. So that's an example of an industrial product and a redesign of such a product that we do to improve its environmental impact. As an example of a new design of a consumer product, this vacuum cleaner has been modified by inserting its motor within a black box configuration, where what you do, the idea is, the concept is called repair at home. So we've done a survey of why the vacuum cleaners are typically either thrown away. In most cases there is an electrical fault and the consumer, the repair of the actual vacuum cleaner is more expensive than buying a new one, so it gets thrown away. But what we're trying to do is, by making the disassembly a one operation, you can extract the motor, you can either take it to be repaired or get a replacement, and at home you can repair your vacuum without having to disassemble the whole of the product. The other concept that has been promoted with this new design thinking is the concept of product for life. The product for life concept is where we are trying to sort of introduce a behavioral shift from these patterns of buying, using, and throwing things away, by having a product structure that satisfies your need, but when your need changes. So for example, in the case of a vacuum cleaner, if you're going into a bigger place, you need more powerful, bigger vacuum cleaner. By having this modular design, you'll be able to reconfigure and change the product structure of this vacuum cleaner to meet your new needs. So having a more powerful motors, having a bigger dust collectors, rather than throwing the actual whole of the vacuum cleaner and getting a new one. Another design projects, all of these, by the way, are student projects. Students in first year, second year, and third year have got different practicals that come in, and sort of depending on the specific practical work that they're sort of focusing on, they'll be able to use these facilities here to do a number of different projects. We also undertake a number of research projects that are typically funded externally by industrialists, and we use these student projects to support that type of a research that we do externally. So this is the work that we've been doing with the microwave. Typically microwave has got a megatron, which is creating the signal that warm up the food, And because this is typically placed in front of the microwave, you need this turntable to be able to rotate the food to bring it in touch with these signals for the food to be warmed up. So the idea here has been that we change the angle of this Megatron and insert these reflective plates in the corner of the internal cavity of the microwave. So what will happen is when the signal is generated, it bounces back of these different surfaces, hence redundant the need for the turntable to rotate the food, because the signals are basically all around this internal cavity and warm up the food without having to rotate it. By doing so, you actually reduce the amount of energy you need to rotate the food, which is typically somewhere between 30 to 50% of the energy that the microwave uses. So inserting those plates, inserting and changing the internal cavity of this plate, allow the amount of energy that is used by the microwaves to be reduced between 30 to 50%. So this is our manufacturing hub. Basically, in this area, what we do is we're looking at the environmental impact of the production processes within, say, a typical factory, looking at the various resources they use, the energy, the water, the type of material you use, amount of waste that they generate. We'll study why, for example, they're generating this waste, how much energy they're using, are they using this effectively? And by gathering that information, we provide the sort of knowledge that you need to improve the design of the process to become more environmentally friendly, more energy and resource efficient. So for example, here is the project that we're doing for the food sector, looking at amount of the water that they use in their different processes like washing, cooking, cleaning, so on and so forth. These vessels are a typical vessels used in food sector, where a range of activities like mixing, cooking, washing and also sort of happens, and typically you've got pipes that the water is, depending whether it's a clean water, dirty water, detergents and also things being introduced into these vessels. We hooked up the vessels and the various pipes with different sensors that measures the temperature in the water, it measures amount of the water that is being passed, it measures the contaminants and the pollutant within the water, and you could kind of just identify what type of wastewater is being generated. The idea in here is to create a set of data on saying how much water is being used, how effectively that water is being used, and what can we do to reduce this amount of intake water to do the same function. And the other particular interest in here is to measure the amount of contaminant and pollution in the water to identify a specific refining process that you need to be able to recycle that water. So the concept of can you recycle the water within the factory without having to take it away and treating it elsewhere. So these are other examples of production processes that are typically you find within a food manufacturing system. You've got the mixers, you've got ovens, you've got the different types of washers that are using water and energy. Again, we'll hook all of these up, measure the amount of energy that they use. We look at the use of that energy, how productive it's been, the concept of embedded energy, so how much energy you use to process one single product. This type of information and knowledge, which is currently not gathered and not available within the production system, help us to look at how efficiency, we are already aware of all of the environmental impact associated with the generation of energy. One of the best ways that we could reduce that impact is to make sure the energy is used in best possible way. And this study of different processes and amount of energy that they use is designed to focus to reduce that amount of energy and make these processes as energy efficient as possible. So in the recycling hub, we either focus on recycling of a high value product when they come to the end of their life. Example of it, like this sat-nav, which has been extracted from a car that came at the end of its life. Now, within this, there are lots of valuable materials, so-called precious material or strategically important material. There are gold, platinum, indium. There are things like hard disk. There are different magnets in this. These are all, if they were dismantled and separately recycled, we can get a high quality sort of material that can be used for other applications. The problem is that if this item is within a car when it's shredded, Majority of these strategically important materials, the precious metals, are in a form of grams within these equipments. So it would be very difficult to extract these few grams of gold or silver or indium, all of the other strategically important materials from a car of about 1.5 ton. So the process is to extract the valuable materials and then also to disassemble these components to its individual sub-assemblies, where then it becomes a lot easier to access those valuable materials and recycle them. However, as you can imagine, this is a costly activity. Extracting the equipment from the car and then extracting the various sub-assemblies from the equipment takes a long time. As a result, in Loughborough, we are working in trying to train the robots to be able to automatically disassemble these components and extract those materials that we are targeting. Now, we use the robot increasingly in our production, and as a result, we have the capability to produce more and more. We see the robots equally useful in end-of-life management of the product, in the recycling of the product, to be able to help us to either remanufacture and reuse the product or extract the valuable materials and help us to then use that material for other applications. So the second type of the product that we're considering in this recycling lab is the products that have got a low hidden value at the end of their life. For example, these shoes. The low value, it refers to the value of the material that you can extract from these products and be able to recycle it and reuse it. Most of the materials are typically low-cost plastics, rubbers, foams, textile. So when it comes to this low hidden value product, obviously we can't use the same processes we use for the sat-nav, where you had expensive materials like gold, silver, indium, and so on into it. With these low value products, what we do is we use a process called fragmentation, which is typically we've got different types of processes: shredding, granulation, pulverization. All of these processes basically take different chunks of the material. They have hammers, cutting hammers, that when you put the product into it, a bit like a paper shredder, it sort of breaks down the product into small particles. And this particle size depends on the resolution of the process that you use and also the filter that you use to allow the smaller products to come out of these shredding and granulation processes. So here are some examples of the shredded shoes that are being shredded based on 35 mil particle size all the way down to 3 mil particle size. The idea about kind of looking at this different particle size is to say, what size do I need to go through for the most of the materials within a particular product to come apart from one another? Clearly, the smaller the particle size, the more likely that the material is separated. However, if you want to actually cut a product to that size of the particle size, obviously you have to then keep the product longer in the shredder or longer in the granulator, so the throughput is going to be small. So you have to strike a balance between the particle size that you need to select and also the time that you have to recycle the product. Having fragmented the product into its small particle size, then you have to use different material characteristics to separate these materials. So all of your plastics and leathers and rubbers and stuff are all now mixed in these shredded shoes. So you need to find different separation processes that allows you to extract your leather, your rubber, your plastics, and your foams apart from that. That is a number of separation processes that we can talk about now. So this is an example of one of these fragmentation processes. This is a granulation machine. Basically, footwear is inserted from the top of this. You have a series of the hammers in here, very sharp hammers, that basically takes chunks out of the shoes and creates particle size depending on the filter that you use at the bottom of this. So the smaller the filter, the longer the shoe stays within the granulation process and gets cut into a smaller particle size. The bigger the filter, the quicker the shoes goes through the granulation, and then you've got obviously larger particle size. And that's a process called granulation that converts the shoe into the small particles, but they're now mixed. So all of our leathers, rubbers, and plastics and everything else are mixed into this, which we need to use a number of separation processes to separate them to individual materials. So this is an example of a post-fragmentation separation process where we're using, and it's called air cyclone. So the idea is that fragmented sort of shoes is inserted into this area where a cyclone effect is generated, i.e. all of the particle size are rotated in a high speed. With this process, obviously, like any other sort of air cyclone effect, anything that is heavier typically gets thrown further from the center of the cyclone, and anything that is lighter gets thrown closer to the center of the cyclone. This way, you'll be able to separate your heavy particles from the lighter particles. So this is your rubber, plastics, and leather, and majority of textile and foam, which are the lighter particles, are separated into these two areas based on this cyclone process. The other process we have in here called air zigzag. So air zigzag works based on the terminal velocity of the particle size. Terminal velocity is affected by the density of the material and the surface area. So the bigger the surface area, the lighter the density, it takes longer for the product to drop. The smaller the surface area, the higher the density, the quicker it would drop. So by introducing the waste into this zigzag sort of a panel, you're delaying the speed with which the various particle sizes are dropping. What we're trying to do is to make sure that the heavier material are dropping quicker and the lighter material are more or less suspended at this area. So having fragmented the shoes into a smaller particle size, we are going to exploit some material characteristics, things about their weights, their terminal velocity, and then separate them into individual material types. So you have the mixed materials when they're shredded, and then you get your leather, your rubber, your plastics, and your foams out of that. And then you can adopt either a further mechanical or chemical processes to recycle the separated material into a range of recycled material that you can use for a number of applications. So for example, some of the rubbers that we have extracted from the shoes are used for athletic tracks. So the top layer had to be obviously painted to be able to represent the typical sort of color of athletic track, but these are all come from recycled rubber. Alternatively, these are exactly the same materials, but are used as an underlay in basketball court, and it gives it the sponginess that it needs in that court. Some of the plastics are being kind of recycled and mixed with virgin plastics and then melted and reconstituted, and you get sort of a raw material, low recycled plastic that you can make a range of products. For example, this is just representing a small frisbee, just to say that if the material is good enough to be used in the toy industry, then it can be used in almost every other industry. You can then further process the separated material. So for example, this is a rubber that has been devulcanized and revulcanized to make it a rubber sheet that then you can use further, use them to make further shoes with them.